Bonjour à tous. Hi everyone. Thanks for being here for this speech. I'm going to talk about geoscience site characterization in geosciences, in offshore wind, sorry. So, my name is Benjamin Souviat. I'm geoscience manager for Oxan Energy, and I will right now start with a short introduction on who is Oxan Energy. So, we are a new developer. The company was officially started last year, just about a year ago, and we became more public on website and social media starting early this year, January. So we are a developer, French developer in offshore wind and more specifically floating wind. The company is built on knowledge and experienced people coming from floating wind industry. We are nearly 20 people in the company now, and we look at all aspects. We cover all the necessary expertise and competencies to lead development from site identification, bid management, permitting aspects, all the engineering elements. We are gathering all competencies to develop entirely a project, and we are supported with our main shareholder, is an investment fund that gives us capacity to be part of partnership and consortium for developing floating wind farms. So our objective as a developer is to join a consortium and take leadership on technical aspects, as well as being an investor, active investor in the development. So this is for Oxan Energy. And now the subject of this speech is geoscience site characterization in offshore wind. This presentation is, I would say, for non-geoscience specialists to understand more broadly what are the main implications, the main scopes that we are looking at in geosciences for offshore wind farm development. And we'll touch base on some specificities related to floating wind as our core business at Oxan. So general principles, I've decided here to split the geoscience topic in three main activities, I would say. The first one is a desktop study as part of site identification and early understanding of site conditions. We look at geological context, constraints, morphological constraints, but not only infrastructures constraints or restricted areas constraints. We can start looking at geohazards as they are known globally, regionally, man-made hazards. So we perform all the site screening elements based on bibliography, public data. In some cases at this stage, we can also have access to non-public data, but historical data, for example, from oil and gas exploration, historical exploration, or from oceanographic campaigns that are not necessarily within public domain, but can be accessed via different routes. And one of the key here in terms of, so we call it desktop study because this is done in office based on information collected in the office. Another major element, and quite often the second stage, is the geophysical site characterization. And this is conducted for two purposes: for environmental purposes, in terms of identification of seabed habitats and species, and also done for engineering purposes. And in the next slides, I will provide a bit more information on what it involves. So in this phase, the objective is the characterization of seabed and subseabed conditions using non-intrusive techniques, except when we can accommodate on the vessel. We'll tend to take sufficient samples or shallow samples, and in some cases, some light geotechnical samples and testing. Another phase is the geotechnical site characterization using intrusive techniques, where we're going to be collecting deeper samples and making in situ measurement to characterize the ground conditions and provide physical and mechanical properties of the ground. All this, and through this process, and we'll talk about it in more details in the next slides, we are going to develop a ground model. And all this is necessary information for developing a wind farm in terms of layout, integration of constraints, designing anchors. Geotechnical information is the key input for the design of anchors. And we need that also to perform the installation analysis of anchors and cables and all the infrastructures that will eventually be on site. So, geophysical survey, for those who are not familiar with it, just checking time. Geophysical survey comprises primarily bathymetry, where we measure water depth in a, I would say, continuous manner across the entire site using multi-beam echosonder techniques, where we get also at the same time, simultaneously with a different tool, with a side scan sonar, we get an imaging of the site, and we identify obstructions such as boulders, wrecks, and we also get the texture of the ground from which geophysicists can interpret the nature of the sediments, whether it's coarse, sandy material, more silty material. In the same time, on the right of the slide, we acquire seismic data, and this typically I wanted to divide it in two types of data, what we commonly call sub-bottom profiler data, which is relatively small, compact equipment, easy to deploy, but limited in terms of penetration depth to the upper 5 or 20 meters. Some equipment provider and companies would claim deeper penetration, but it's not always the case. It's quite dependent on the ground conditions. The other technique is what we will call ultra-high resolution multi-channel seismic or 3D seismic, which guarantees a deeper penetration and a deeper understanding of the stratigraphy and geological conditions. From the seismic elements, so the right part of the slide, we'll get the subseabed stratigraphy. These are seismic reflection methods that allows identifying the variation of stratigraphy across the entire site. Now, a few words about geotechnical survey and what this involves. There's two types of geotechnical investigation methods, two main families, I would say. One is what we call seabed investigation working in a seabed mode, where we're going to lower an equipment on the seabed, and this equipment will operate with maximum capacity, is operated from the vessel, but is only connected to the vessel with an umbilical that provides power in many cases and provides data transmittal to the vessel. But there's no mechanical connection between the equipment and the vessel. So we can only operate to its maximum capacity. On first picture is showing a light type of a seabed CPT system, which is a cone penetration testing equipment that that pushes an instrumented cone into the ground to measure physical characteristics of the ground. And the one that we see on the bottom is a vibrocore, which is a type of sampler that once we lower it on the seabed, vibrate it, penetrates into the seabed up to 6 meters, and once it's retrieved, it keeps the sample into the tube, and then we bring it back to deck to get the sample. What we see on the right is the drilling system, or downhole system, where in this case, as we can see, there is a mechanical connection between the vessel or the self-elevating platform, the jackup, with a drilling system, and we operate the tools, whether cone penetration tools or sampling tools, into the drilling, into the drill string, which then makes the main differences and limitations of these two techniques. Seabed mode, as I was saying, the penetration is limited to the capacity of the tool and to the ground conditions. If the cone hits a hard layer or a buried boulder, the equipment cannot push further, the test is stopped, and we cannot go deeper. In a downhole mode, there's practically no depth limitation, in the sense that we can drill through hard layers. And when I say no depth limitation, is with regards to the depth of interest we are looking at for offshore wind farm site characterization. We're looking at depth of interest of 30 meters to 50 meters below seabed. In both techniques, we can use, as I was saying, cone penetration testing. We can include in it seismic measurements of shear wave and compression wave velocity in the ground, which is a relevant parameter for engineering. We can measure the thermal resistivity. In downhole sampling, we can perform some more advanced downhole geological and geophysical logging with specialized tools. We can perform also some pressure meter tests or high pressure dilatometer tests to gather some specific mechanical properties of the ground. So we can do quite a long suite of use quite a long and varied series of techniques, either downhole or in seabed mode. And importantly, for any geotechnical site investigation, we also have an onshore laboratory testing that is very important to characterize the physical and mechanical properties of the ground. So it means that we're testing in specialized laboratory the soils, the samples that have been collected during the site investigation. Then through this process, as I was mentioning earlier, we also develop what we call a ground model. So most people, and I imagine you have heard in the context of geoscience, you have heard about ground models. What is a ground model? It is a representation of surface and subsurface conditions, and this is built by integrating both geophysical and geotechnical information in a consistent geological framework. Hopefully this is illustrative enough. What we see here is a seabed, an image of the seabed comprising bathymetry and texture characteristic of the seabed. We have a grid of seismic lines which provides this type of information. We see the reflectors, which are then interpreted as different soil formations. Is a representation of the stratigraphy of the ground, which we correlate then with geotechnical information. This is typically a CPT con penetration test profile that provides a mechanical, here in this case, con resistance variation with depth, from which we can identify different layers, which hopefully will match with this stratigraphy. And we integrate all that in a volumetric model of the ground, where we can see the stratigraphy, the changes in color that represent the different layers. And to each of these layers, we can then assign geotechnical properties that have been measured across the site. We call it a 3D model. This representation is a 3D model. In practice, we use a 2D representation, most of the time GIS-based type of software, to which we can assign properties with depth. The 3D aspect of the model is more a graphical illustration of what we get in a 2D model with values assigned with depth, if you see what I mean. Ground model is evolutive. We start building it with the very first studies that I was mentioning earlier, the desktop studies. We start building a database of what we know of the ground conditions, and then we integrate the first geophysical results in a seismostratigraphic model. And then we start building in the geotechnical information to build a geological and geotechnical model. So it is evolutive, and it is very important to manage this flow of information as it comes through and update ground models as new data becomes available. You may have heard about predictive ground models, synthetic CPTs. There's been a lot of talks around it. It is a way of extrapolating geotechnical information at locations where we don't have this geotechnical information, but we have geophysical information. And within this information, within this data, there's not only reflectors, but some attributes that can allow, to some extent, using machine learning techniques, to predict ground conditions anywhere across the site where we have seismic data along the grid. So, as I said, it's a lot of talks around it. Is extremely powerful. It can allow, well, by extrapolating data, to reduce to some extent the need for geotechnical investigation in some cases. Whether this can replace or not geotechnical information is a big debate at the moment. There are some discussion about allowing, possibly certifying extrapolated site data and not strictly requiring geotechnical information for final geotechnical design. But that's up in the air, in discussion, because even though the technology and the scientific knowledge and the information is there, it still poses a risk associated with a lack of geotechnical data. And when it comes to installation, who bears this risk? So then it's more of a risk management consideration within a developer, I would say. So now we've talked about all these sequences, all these main blocks of desktop study, geophysical and geotechnical campaign, and ground model development. How does that fit within project? I've decided here to mention, in terms of surveys, preliminary geophys and preliminary geotech. It doesn't mean that they are light. It doesn't mean that they are rough and crude. It means that it's the first one that we do on the site. And as I was saying, from a desktop study, we have an initial ground model. And from this, we can do conceptual anchor design, typically. Start defining what is feasible and what is not at a broad scale. From a preliminary geophysical survey, we get a seismostratigraphic model from which, especially if we have some understanding of geotechnical conditions, we can start looking into preliminary anchor design. And the objective here with this preliminary geotechnical investigation is to collect a sufficient amount of geotechnical information to build a robust ground model from which we can get into quite an advanced level of engineering, the FEED engineering, front-end engineering design, with robustness, I would say. But at this point in time, the field layout is not known, so we haven't yet investigated precisely at each anchor location. We have characterized the ground. And there's kind of a consensus, I would say, in the offshore wind, whether fixed, bottom fixed, or floating, in the fact that we need this level of information and we need to have a robust ground model to get to FID, financial investment decision. But where there's a lot of, not so much debate, but site-specific consideration, developer-specific consideration, appreciation of risks, is where do we fit in terms of CFD, bid, auctions? What do we need to propose to develop a reliable preliminary project, to propose a price associated with it? And actually, where we have one block of geophys and one block of geotech, it may be that these are split into different phases. It depends on what state agency will provide at what point in time. If we are in how to say, in a situation like in France where state agencies will provide preliminary geophys and geotechnical data to make sure that at the bid stage the price is well constrained. The technical choices are well constrained and the price that comes from it is well understood. And that's what here cannot be written on the paper because it's specific to each country, what is provided at what point in time, and also what is the appreciation of risk and uncertainty, and that's what we have a graph on the right. Finding the right balance and the fine-tuning between the amount of site investigation information, the cost that goes with it at an early stage of the project, investment at risk, and the geotechnical risk related to the level of uncertainty that we have. So I see that the time is turning, so I'll be quick on the last two slides. The other way around. There's innovation happening these days in the field of geoscience site characterization. We see quite a few on the stands around us about unmanned surface vehicles for geophysical survey, lean crew vessels in the sense that we can try to reduce the amount of crew on board to some extent for both geophysical and geotechnical surveys. There's a lot of permanent development in geophysical survey tools. Just to mention a few, we have a discussion. We hear a lot about SAS, synthetic aperture sonar these days, use of 3D seismic data more generally, the use of electromagnetics for detecting subseabed heterogeneities where traditional techniques fails, um, predictive ground models. We've touched based on that. And the use of machine learning for data processing. But let's keep a few minutes now to talk about some of the challenges that we're facing in floating wind. So floating wind in deeper water than what we have for bottom fixed means also that we are often further away from the coast, so we are in a less known territories from what has been investigated with a hydrographic survey and common public understanding of the seabed conditions, both from environmental perspective, seabed habitats, but also from an engineering perspective. There can be some level of unknowns in terms of sediment dynamic processes and etc. And also, as we're moving away towards towards the edge of the continental shelves or into the continental slope, then we can start facing issues with geohazards such as submarine canyons, landslides, and all sorts of exotic features. Also, just a quick word on the fact that as we go towards unknown territories, we have to stay vigilant on some of the elements and risks and hazards that we don't yet know of, but we know that we have faced them in the past in geotechnical history of oil and gas development, and recently in offshore wind development as well. And just for the few examples, carbonate soils and weak calcarenites in Australia, which have caused serious troubles in the, was it in the 80s and 90s, I would say. Recent pile runs in Taiwan, and some, just to say that there's always, we cannot predict the unpredictable, and we have just to be conscious of it and stay vigilant. And just a last word to say that next year there will be in Nantes one of the major offshore conference in offshore geotechnics is FOG. So if you are interested with offshore geotechnics, that's one of the major worldwide events, and it will be held in Nantes next year. Thank you for attending. Thank you for being here. Very pleased to see that floating wind, the core business of Oxan, is very well represented and brings a lot of interest. Apologies, we don't have time, I think, for questions, but if you have questions, you can come at our stand, booth F06, towards the other extremity there. Thank you.
Thank you.